Okay, so today I'll be explaining the process of DNA replication. So right here we have a strand of DNA that's 5 rungs long, the 3' end being here and the 5' end being here. Now how this begins is an enzyme called helicase binds to the DNA and causes it to break up as so. Once the helicase has broken up the DNA strand into 2 single strands, certain proteins called single-strand binding proteins that look like this bind to the end of each DNA strand in order for it to not go backwards into the helicase, just like so. Once the single-strand binding proteins are on the end of each DNA, you can now begin the process of DNA replication. So, replication begins at the 3' end of each DNA, meaning the 3' sugar on the backbone, such as right here, and the 3' end on the sugar right here that's covered up by the protein. Right here. Okay, so how it all begins is there is a leading strand, which means the 3' end is going away from the helicase, and the lagging strand, which means the 5' end is going away from the helicase. So let's begin with the leading strand right here. So how it works is a protein called RNA polymerase binds to the DNA strand at a certain point. And what this is going to do, it's going to connect a complementary RNA base to the DNA base in order to show the next enzyme, DNA polymerase, to show where it should begin in order to connect each base to its certain complementary base, like as so. Once the RNA segment is binded to the DNA leading strand, which is once again the 3' end, the primase can then leave and a new enzyme called the DNA polymerase 3 is used to attach individual bonds onto the new bases. So T always pairs with an A, like originally, and A pairs with T, and C pairs with G as G pairs with C. So in order for T to combine, it must use an A. And the A has 3 phosphates because it needs the energy to get there. So once it gets there, it uses its 3 phosphates, like so, to fold over, and then it combines to the T. After that, the DNA polymerase 3 then moves on to the C base and attaches the G, once again using 2 phosphates in order to power the process. Then it connects a T segment to the A, once again using 2 phosphates. And then finally, the DNA polymerase connects a new C base to the G base. So, on the lagging strand, the process is a little bit different, since it has to go from 3 to 5' end, just like the leading strand. But the problem is the 3' end is closest to the helicase, while the 5' end is over here, and it gets a little fragmenty while the process is occurring. So it begins with an RNA polymerase, just like on this side, to connect an RNA base, which would be the G to the C, in order for the DNA polymerase 3 to know what bases to connect to each new ones. Now, the DNA polymerase can use the base G to help it follow what bases it needs to put for the next 2. But unlike the leading strand, which can then just go and do all the rest of them, the DNA polymerase 3 can only put them in fragments, such as fragments of 3. So it'll first bind the new A to the T and uses the phosphate groups again. And then we'll bind a new C to the G. Once that fragment is put on, another RNA will have to be implemented by RNA polymerase in order for another fragment to be added on to the lagging strand. Since this is an A U base will pair with it, which will give the DNA polymerase 3 a template in order to finish the fragment. This time, since there's only one open base, the DNA polymerase 3 will connect only a C base to the G. The DNA somewhat looks now complete, but a few more steps are needed to take to make sure it is perfect. First of all, a new enzyme called DNA polymerase 1 is used in order to take the RNA bases and transform them into the corresponding DNA bases, such as shell. The DNA polymerase 1 will attach here, cause this G base to detach and form into a DNA G base, such as so. The DNA polymerase 1 works the same on the lagging side as it does on the leading side, such as it'll take this G RNA base right here and convert it into a G base of DNA. And finally, the U RNA base will be taken up by the T, which would be the corresponding DNA base. Like so. Now that all DNA bases are there, the final step can be done. As seen here, each part of the nucleotide is bonded by a phosphate sugar, also known as a phosphodiester bond. On the new parts of the new strands, though, there is no bond between these two. So, an enzyme called DNA ligase is used to attach each new nucleotide to each other with phosphodiester bonds, which I have no visual representation of, so I'll show you a quick clip of me taping them together. Now that all steps are complete and all nucleotides are paired correctly to the correct base and now have phosphodiester bonds between the two, the original proteins can be taken off the top. As the DNA moves away from the helicase with its two new strands. Thank you for watching.